In this lesson, we're going to look at combining random variables. Earlier in the year, we looked at how measures of center would change if we added or subtracted constants to them. We saw that adding and subtracting would change our measures of center, but how spread apart your data is would not change. Now, multiplying would change our measure of center, and it would also change our measure of spread. So the one that I always told you to remember was that adding or subtracting wouldn't change the variation, and we looked at small sets of numbers. So when we are changing a random variable by a constant, okay, so just a regular number, these rules that we've already talked about will still apply. So here's the new part, okay? So when we're combining two, first of all, they have to be independent random variables. These are the rules we're going to apply. Adding and subtracting, no big deal, okay? We just add our two random variables together to find the new mean. If we are subtracting two, we just subtract the means. Now, the variation is a little bit different. So when we're finding the standard deviation, we can't just work off of our standard deviations. We have to work off the variance. And remember, the relationship is just your standard deviation squared. So what you do is when you're told to find the new standard deviation, you're gonna add the variances. And if you're told to subtract two random variables and you're finding your new standard deviation, you're actually also gonna add them, which is gonna throw some kids off at first. And here's the reason that you're always gonna add. If you're combining two random variables, your variability is not going to decrease. It's actually going to grow. It's going to increase, which is why we're always going to add our standard deviation. And we'll look at this and make more sense of it with some examples. I need to emphasize, though, that our variables absolutely must be independent in order to combine our standard deviations, or to work off of the variance, that is. If they're not, we cannot do it. So we're going to look at a completely algebraic example here, where we're given two independent random variables with their means and standard deviation. And we are told to find the mean and standard deviation of several different scenarios. So completely algebraic, no context. So for the first two, we're going to be using the rules for adding and subtracting constants. So just put them here on the screen to remind you. So what are we going to do? Well, to find the mean of our random variable minus 20 is going to be, well, how does that affect our measures of center? Well, we just add or subtract from it. So we're going to do 80 minus 20 is 60. All right, how about the standard deviation of x minus 20? Well, that's this scenario here, and measures of spread are not affected by adding or subtracting a constant. So this is going to stay at 12. Okay, next we're told to do 1/2 or 0.5 times our random variable. And multiplication and division, you can see here, affect both measures of center and measures of spread. So I'm going to do 0.5 times 80 would be 40. And for my standard deviation, I'm going to take 0.5 times 12 to get 6. Okay, so let's look at the next three examples, which hopefully you realize you are combining two random variables, because capital X plus capital Y. So with finding new means, there's not really anything particular that you need to remember. There's nothing tricky, I should say. So 80 plus 12 is 92. All right, now let's talk standard deviation of x plus y. So I'm trying to write that as a subscript, although it doesn't look too much like a subscript. I have to work off the variance. I can't just add two standard deviations. So the variance of x would be 12 squared, plus the variance of y would be 3 squared, and then I'm taking the standard deviation excuse me, I'm taking the square root to get the standard deviation. So this would be the square root of 144 plus 9 would be 153. And throw that in the calculator, and I get approximately 12.37, which makes sense. You know, I'm combining two random variables. I would expect my standard deviation to grow somewhat. Now, I'm going to subtract two random variables, so mu of x minus y. Again, the means, nothing really special to memorize here or tricky. Rather than just memorizing, it's always good to understand where things come from. So this would be 68, and the standard deviation of x minus y is the same as the standard deviation of x plus y, okay? Because if I'm combining two random variables, I would not expect that there would be less variation. I would expect that there is more variation. So your variation is always going to increase when you combine two random variables. So again, I work off of the variance, and honestly, we just did this. It's going to be exactly the same as what was above. So it's the square root of 153 again, which is approximately 12.37. And lastly, in my algebraic example, I'm showing you y1 plus y2. So this means that I'm combining this random variable with itself. So this would be equal to just 12 plus 12, or 24. And standard deviation of y1 plus y2, my variation, is going to grow, all right? But I work off of my variance, which is the standard deviation squared. So it would be 3 squared plus 3 squared, which is, just give myself a little more space to write, the square root of 18, or approximately 4.24. Now, I think that these examples now will help you make more sense of everything by revisiting your textbook example with context. Okay, so we've determined that couples dining at the Quiet Nook can expect Lucky Lover's discount averaging $5.83 with a standard deviation of 862. Suppose that for several weeks, the restaurant has also been distributing coupons worth $5 off any one meal. And they say there's one discount per table. So if every couple dining there on Valentine's Day brings a coupon, what will be the mean and standard deviation of the total discounts they receive? So in our last video, we had built a probability distribution using capital X, our random variable, was the amount of discount. So what we're saying is, what's going to happen if we add 5 to every person dining there on Valentine's Day? So we're going to compute our new mean. Well, you don't need the raw data, you just need the previous mean, which was $5.83, and we add 5 on it to get $10.83 for the new average amount that couples can expect. How about our standard deviation? Well, standard deviation of x plus 5 is the same as the standard deviation of just x. Adding constants to our standard deviation does not change our standard deviation. Remember, the easiest way of looking at that is if we had numbers that were like 1, 2, 3, 4, 5. How far do these values typically vary from the mean? If I add, let's say, 5 to each of them, 6, 7, 8, 9, and 10, how much, my new mean would be 8. How much do they typically vary from the mean? Variation's not changing, okay? So that's why it's remaining the same with constants. So it's still $8.62. So I'm stating that couples with the coupon can expect total discounts averaging $10.83. The standard deviation is still $8.62. So let's expand on this scenario further. So again, couples may get a lucky lover's discount averaging $5.83 with a standard deviation of $8.62. But when two couples dine together on a single check, the restaurant doubles the discount offer. Doubles the discount offer. $40 for the Ace of Hearts on the first card and $20 on the second. What are the mean and standard deviation of discounts for such foursomes? Okay, so what are we doing if we're doubling our discount? That's saying we're doing 2 times our random variable was our discount. So we're going to find our new mean, which would be 2 times the $5.83 or $11.66, and our standard deviation since we're working with a constant, we're just going to double our standard deviation. So it's only adding and subtracting, that doesn't change the spread of data. So this would be $17.24. So if the restaurant doubles the discount, two couples dining together can expect to save an average of $11.66 with a standard deviation of $17.24. Okay, let's expand even further. So same mean and standard deviation. And we've seen if the restaurant doubles the discount offer for two couples dining together on a single check, they can expect to save $11.66 with a standard deviation of $17.24. Some couples decide instead to get 2 separate checks and pool their discounts. So it says, you and your amour go to this restaurant with another couple and agree to share any benefit from this promotion. Does it matter whether you pay separately or together? So we just saw the $11.66 and the $17.24 as a result of paying together on a single check. So let's look at paying separately, but then combining our discounts. So if we do that, that would be 2 random variables. Okay, so I'll say capital X1 plus X2. So that's going to be equal to just add our 2 random variables together. So the 583 and 583 would be $11.66. So the expected savings is $11.66 if you pay together, or now we see if you pay separate and pool your savings. Okay, so let's look at the standard deviation of paying separately. So this would be the standard deviation of x1 plus x2 is equivalent to, we have to work off the variance, so the square root of 862 squared plus 862 squared, which would be the square root of about 148.6088, which is approximately $12.19. So this standard deviation is lower if you pay separately than together. So my conclusion here is when couples get separate checks, there's less variation in their total discounts. The standard deviation is $12.19 compared to $17.24 for couples who play for the double discount on a single check. Now, one thing that I need to go back and just stress right here, before I even find my new standard deviation, I really need to address the idea of independence. So I really should have put a sentence in here. Forgive me, sometimes when I'm recording, my brain's not working as I'm trying to figure out my tech tools. But what I really need to state is it independent? If they're not independent, I can't just combine 2 random variables. So let's think about it. Well, the cards would be reshuffled after each couple's turn, so the discounts that the couples receive I would expect to be independent. So therefore, it's okay to add the variance. So it'd be really good to put a sentence in there addressing that independence. And again, let's look at a slightly different scenario. So we still have the 583 and 862 at the Quiet Nook. But just up the street, the Wise Fool restaurant has a competing lottery of love promotion. There, a couple can select a specially prepared chocolate from a large bowl and unwrap it to learn the size of their discount. The restaurant's manager says the discounts vary with an average of $10 and a standard deviation of $15. How much more can you expect to save at the Wise Fool, and with what standard deviation? So I like to put this into notation to help me really process what I'm being asked to do. So I'm going to say that my X was the discount at Quiet Nook, like it's been the whole time, Quiet Nook. And I'm going to say capital Y would be the discount. Again, it's a random variable, depending on the chocolate you pull out, discount at the Wise Fool. All right. So how much more can you expect to save at the Wise Fool? So expected value is our mean. So we are doing the expected value of subtracting, other way around, Wise Fool would be more. So Y minus X. And that's the same as the mean of Y minus X. So what do? I just subtract the $10 minus the $5.83 would be $4.17. How about the standard deviation? So the standard deviation of Y minus X is equal to the standard deviation of Y plus X. Why did I just change it to addition? Because if I'm combining two random variables, again, I wouldn't expect for my variability to decrease. I'm combining two random variables now. I would expect my variability to grow. Okay, so I'm going to end up adding the variances. So I do the square root of the new standard deviation was 15, so 15 squared plus the one we've been working with the whole time would be 862 squared. And I'm going to toss this in my calculator, and there it is, $17.30. So discounts at the Wise Fool will average $4.17 more than at the Quiet Nook, with a standard deviation of $17.30. Okay, so again, same old thing with the Quiet Nook. And the restaurant owner is planning to serve 40 couples on Valentine's Day. What's the expected total of the discounts the owners will give? All right, so what are we doing here? I will be combining 40 random variables, okay? So we are not doing just 40 times something. It's not a constant. Each couple is randomly getting a discount. So it's 40 random variables. So what's the expected total? Okay, so expected total of adding x1, x2, and I'm not going to sit here and write it out 40 times. I'm going to say up to x40. Now, I will tell you that occasionally you'll see something like them. You'll see it defining another variable where you'll say t is equal to x1 plus x2 plus x3 plus an ellipsis up to x40, and then you can just use e of t. So it's kind of personal preference, whatever you like. So I'll just work this out with a t now to help you understand. All right, so what am I doing? This would be equal to 5.83, and I'm going to add this together 40 times. Okay? Now, mathematically, is that equivalent to 40 times? Well, yes, this one is. So what you actually type in your calculator could be times 40, but I'm going to write it out like this so you recognize why I'm adding it. I'm using my rules for random variables. Okay, so the expected discounts would total $233.20 for 40 customers. Now, reshuffling cards between the couples would make my discounts independent. And why am I addressing independence? So that I can combine my variances to get my standard deviation. All right, so since I've addressed independence, now it's okay to proceed to find my standard deviation. So sigma of my total, just using that t again, would be equal to my standard deviation squared. And I would write this out 40 times, but I'm not going to write this out 40 times because I'm going to run out of space. But now I can think about, okay, so what would that mathematically be equivalent to? So that's going to be the same as 40 times $8.62 squared. Okay, so only the $8.62 would be squared. And I'm going to put that in my calculator. And let's see, I get $54.52. My conclusion is that the restaurant owner can expect 40 couples to win discounts totaling $233.20 with a standard deviation of $54.53. So I encourage you to study your rules. Big picture would be subtracting the standard deviation of random variables is equivalent to adding. It's always going to grow with your variation. Always work off of the variance when combining random variables for standard deviation. And make sure you are clear in your notation that you're not applying rules of constants instead of rules of random variables. It's time to practice.